Polaron. So what I'm going to talk today is about all the results we got in the group of Cesare Franchini with the support also of Georg Kresse, performing density functional theory calculations at the University of Vienna, and in collaboration with the experimental group of Ulrike Diebold from the Technical University of Vienna. As you already heard from Martin Setting yesterday, they mainly perform surface-sensitive experiments, especially atomic force microscopy and scanner tunneling microscopy. So what can we do with density functional theory? I know we have already looked at this kind of sketch many times, and this is my sketch, where with density functional theory, we can basically obtain two different solutions, one with the electrons that are delocalized and kind of equivalently shared by equivalent atoms, and another solution with the polarons, where the charge is localized somewhere and there are distortions of the lattice around it. These two solutions have different energies, and the difference in energy, we call it polaron formation energy, which describes the convenience for the system to form polaron if this energy is negative, or not if it is positive. I would like to add something more, which is that we can also obtain more, because we can obtain more different polaronic solutions, not only the ground state, but also other ones, which are in general not as convenient as the polaronic ground state. And there is no guarantee that our DFT code leads us to the polaronic ground state. This is something we have to do by ourselves, to put a lot of effort, trying to identify which one is the polaronic ground state. And we have heard in the last days many different methods which can be used to systematically investigate different polaronic configurations. And I will talk also about another method that we used, which is the molecular dynamic simulation. Once we identify the polaronic ground state, then we can move to describe the properties of a system. If we would describe or try to describe the properties of the system starting from different polaronic configurations, we would, and actually we did sometimes, obtain completely different results, sometimes also opposite results. So it's very important to identify the polaronic ground state before we move to describe the properties of the system. Okay, this was kind of a short introduction. The outline of the talk is such that I will discuss in the first part about more consolidated results, consolidated because we're published already and discussed by Martin yesterday. So I'm gonna keep it very brief, but I'm gonna try to give some more motivations behind all the phenomena that Martin showed yesterday. In particular, I'm talking about polaron formation in rutile titanium dioxide surface, and two effects that polarons have on the surface, which are the surface reconstruction, structure and reconstruction, and the interaction with the adsorbate CO, as shown yesterday, but also molecular oxygen. Then I hope I will have enough time to talk with calm about very new results, which I guess we have never discussed anywhere, or at least I haven't, about potassium tantalate perovskite surface, which explain also why I called this talk intrinsic in the title. So let's start with the rutile titanium dioxide. This is our model for the system. As we all know, titanium dioxide is a semiconductor with valence and conduction band, but it's very likely to form oxygen vacancies on the surface, as imaged by atomic force microscopy. Here there are missing spots in these rows, which correspond to oxygen vacancies. The oxygen vacancy donates two electrons to the system, which are able to form polarons on the titanium side, as also imaged and shown already yesterday by scanning tunneling microscopy on the field state of this compound here. So if we look more carefully, we notice that these spots have actually a double lobe feature, which can be explained if we model our polaron to be on the subsurface layer, which I call S1, while S0 is usually the surface layer. And if we model the polaron here, we see that most of the charge, kind of 70% of the charge, is localized on this side, but there is a considerable part of the charge which spreads on the surrounding titanium atoms, in particular these two, giving rise to this spot on the simulated STM, which correspond to the experimental STM. If we will model a polaron on the surface layer, which is here, on the side view and top view, you see that these are a completely different orbital symmetry, not even parallel to the titanium rows. So on the STM, we will obtain something completely disagreement with the experiment. And this tells us also something more. It tells us that actually this broad charge here is important. And I let you notice immediately that here we have a distribution over 3 sides in the S1 layer. This will come important in a few slides. And for the moment, I want to mention that this polaron is also predicted to be more stable than a polaron on the surface by density functional theory calculation if you consider carefully your parameters that you use for the exchange correlation correction and also for your lattice structure. So let's move on. Let's consider what is important in this system. First of all, the interaction with the defect and the polaron, which was shown on the first day by Aaron Deskin, who considered the hydrogen donor, and he showed that polarons basically like to stay, the polarons are attracted by the donor, and the same happens for the oxygen vacancy. In fact, when the polaron is far from the oxygen vacancies, the polaronic peak is shifted towards higher energy, while it becomes deeper and deeper as soon as the polarons moves closer and closer to the vacancy. This is for polarons on the sublayer surface. The same happens on the surface layer, with the big difference that there is one side which is much more convenient than the others on the surface, and this side is close to the oxygen vacancy. And therefore, polarons are more likely to hop on this particular side on the surface than any other one. The other interaction, which is important to consider, is the polaron-polaron interaction. Here, the polarons were put at different distances, and then we calculated the energies, both considering polaron in the surface layer and polarons in the subsurface layer. And if we have polarons that are far enough, the interaction is weak. There is still some interaction. It's not yet converged, but we were already at the border of our lab. We couldn't go further away. But the energy levels of the two polarons are the generating energy. So you observe a very sharp peak here. If you put them closer and closer, you come to a point where the two broad charges overlap. And this overlap determines the splitting of the energy level. So now instead of a broad peak, you get a more structured peak. Actually, it's split in two. One important thing, we didn't manage to put polarons even closer than that. So we reached the distance of 6 angstrom, which correspond to 2 lattice sites. We didn't manage to put these polarons just next to each other because the overlap would be too strong and the energy will be too bad. Actually, you can, if you put an oxygen vacancy on top, you actually can, but I'm not gonna discuss about this now. So we perform molecular dynamics on this system, which kind of confirm our expectations based on these calculations on the energetics of the polarons. And in fact, if you calculate the polaron-polaron correlation function, which basically counts how many times two polarons were found at a given distance, we found that a low concentration of oxygen vacancies, so low concentration of polarons, they like to stay far apart from each other, which is kind of trivial result. The maximum distance is 4 sites in our slab. And therefore, we observe that most of the time they are at this distance. If we now increase the density of polarons, we see that this peak moves toward lower value, of course, because they still like to be far from each other, but they can't because there are too many of them. And at this distance of 3 lattice sites, we don't have this overlap. Here we have 2 polarons at 2 sites and overlap. If we have polarons at 3 lattice sites, there is no overlap. So it's still good for them to be in this configuration. If we now increase the density of polaron even more, then what we obtain is not that this peak moves towards lower distances. That will determine a strong interaction of polarons, but actually this peak stays here, and what happens is that polaron starts to populate more and more often the surface layer. So the density in the subsurface layer stays fixed in 1 polaron every 3 lattice sites, which we call 3x1 pattern, such that they do not overlap much. This has an important impact, which was shown already yesterday by Martin, because Rutile is known to reconstruct the surface. When you sputter and anneal the sample, you can create this oxygen vacancy on top, but there is a chemical concentration of oxygen vacancy, which is 17%. After that, the system changes the phase and goes to a 1/2 phase, and these stripes appear, which can be modeled by this titanium-2 oxygen-3 model. But if you calculate the energy with density functional theory, you never find this structure to be stable unless you consider the presence of polaron. If you consider the presence of polaron, actually, you can describe this phase transition. Martin yesterday showed the phase diagrams. I'm not going to show them again. What I'm going to show actually is how the polaron energy changes when you increase the oxygen vacancy concentration. This is kind of a convex hull, which tells us that is in this first part of the graph, the system likes to have more and more polaron, because when you add more system, the polaron formation energy gets stronger and stronger, up to reaching this critical concentration of oxygen vacancy, which corresponds to having a density of 33% polaron in the sublayer. When you reach this point, putting more electrons in the system leads to the formation of polaron on the surface layer, which is energetically unfavorable and does not correspond to observed concentration of oxygen vacancies in the experiment. So this was a very nice result, which showed how the actually forming polaron on the reconstructed surface is more convenient than continue to create oxygen vacancies and forming polaron. But it was actually very expensive to obtain. There was a lot of calculations to be done, because every single point here is not just a single shot density functional theory calculation, but we had to be sure that these points were the ground state of the system, the polaronic ground state, at every different concentration of oxygen vacancies. And to do that, what we did was to take our data from the molecular dynamics, extract the polaronic configurations, calculate for each of them the energy with additional density functional theory calculation at 0 Kelvin. So we did kind of, on top of the molecular calculation, again, thousands of calculations for the energy, extract all the results and put them in this graph. What we are trying to do now is to obtain this graph with less effort, much less effort, via a machine learning approach. There is a master student in our group who is called Viktor Bishiski, who is working on that. So basically, he takes the information on the polaronic configuration from the molecular dynamics, and he's creating a machine which is able to reproduce the energies without actually having the need to calculate them by density functional theory. So obtaining the energy with a faster and less expensive approach. And here there is a comparison between the energies obtained by machine learning and the energies obtained by the FT, and they kind of fit quite well. Also, he already calculated the convex hull and compared it with the density functional theory convex hull, and the agreement is pretty good. I think this, as a very fresh result, of course, can be improved, but I think it's the good way to go. The important thing here is that we choose the important ingredient for our machine. So we have to carefully consider which are the interactions that are really important to determine the energy of our system. And we already looked at them. It's the presence of polarons in the surface layer or subsurface layer, the interaction with the defect, and the polaron-polaron interaction. Once we have these three ingredients, then we can predict quite well the energies. And another thing we can do with machine learning is actually to predict also where the polaron localizes, given just lattice distortions. So, so this is a step even further, where we require even less DFT calculations. Okay, this was just a bird's eye view on this new approach we are investigating now, and now I move on another effect that we analyzed on regarding polaron on TiO2, but gonna be fast as well because this was already shown yesterday. We put basically CO. This is the ground state of the polaron for the clean surface, but when the CO arrives, actually the polarons prefer to stay on the surface just below the CO molecule. And here is the picture that Martin showed yesterday, showing that these two have a very different signature in the experimental and density functional theory STM images. So it's very easy then in the experiment to distinguish between these two cases. And show here also the energy. And actually, you see the big difference of having a polaron on the surface layer without CO and with CO. This becomes now the new ground state for polarons when you put the CO there. But it's not that easy, because you need to consider that the polaron is at the beginning localized on the subsurface layer and needs to hop to the surface layer. And it's true that when there is a CO, this barrier is reduced, but it's still there. So it's not that obvious that you will reach the ground state as soon as you put CO there. And in fact, you see that at low coverage, we still have oxygen vacancies, low concentration of oxygen vacancies, we still have a lot of weak spots which correspond of having no surface polaron below our CO molecule. Because if you look at this problem from the point of view of the adsorbate, so from the CO, you see that the absorption energy show convenient energies for the CO and a polaron underneath, but also for a CO adsorbing on the oxygen vacancies, and for a CO adsorbing far from both the polaron and the oxygen vacancies. So that's why here we get all this type of absorption site. But when we increase the concentration of oxygen vacancies, then we get rid of these convenient sites here, and we are left only with CO adsorbing close to the oxygen vacancies, so like in the oxygen vacancies and close to it with the polaron just below. So that's why now we move to an image with a lot of bright spots. And because of this transfer from the polaron to the CO, we observe a change also in the vibrational frequency of the molecule. And here, if we exclude all the cases that are not convenient in energy, we are left with two classes, one for CO far from the vacancy, one for CO close to the vacancy, and then what we expect from an infrared spectroscopy experiment is that we obtain two peaks, actually, for these two classes. And this is what was obtained a long time ago by the group of Christoph Wall, where they perform infrared spectroscopy on CO on a perfect rutile without polarons, without oxygen vacancies. They got one peak. And when they reduced the sample, they got polaron-CO interactions, and they got two peaks. One thing I want to mention is that this charge transfer is not complete towards the CO. It's bright spot, but the charge transfer is little. And in fact, if you do STM consecutively in time, you see that CO can diffuse with the help of the tip, and the polaron can follow the CO diffusion or cannot, can dissociate from the CO and form another polaron somewhere else, which is, all these examples are shown here. For example, here there was CO without the polaron, weak spot, moving, and then became bright spot. So the polaron hopped towards the CO. And there are other processes also shown by these arrows here. This is completely different from another type of adsorption, which is oxygen molecules. And here you see that the charge transfer from the slab to the adsorbate is it's much stronger. If you look at the density of state, you see that the titanium have a very weak contribution to this electronic state, and everything is on the oxygen molecule. So I wouldn't call this polaron anymore. This is just the polarons leave the surface and go into the molecular orbitals. This was shown by in a poster by Igor Sokolovich, which also was able to identify that these molecules are actually peroxo based by density functional theory energies and also by a comparison of the geometry with the experiment. If you consider this species peroxo, the geometry is in agreement, otherwise not. So, okay, this was it for this part. Since my time is almost over, I'd like to skip the summary and move to talk on the new results, which are more exciting for me. So, intrinsic polaron on potassium tantalate. Potassium tantalate is a material that we started to take under consideration 1 year ago or 2 years ago, because in the lab of Martin, what they did is to take this material, cleave it, and what they observe is the formation of terraces of tantalum dioxide, here in white, and islands of potassium and oxygen here. It turned out that this surface is not very stable, and if you give some kinetic energy to the surface, it likes to reconstruct and arrange in stripes. So you have here stripes of potassium, oxygen, and stripes of tantalum, oxygen 2. Also, with density functional theory calculation, we explain why this happened. And actually, I think the agreement was pretty good, and we did not consider polarons at this time. But what I want to talk now is actually what happens when we start to consider polaron for this system. In particular, this system can form small polarons on the tantalum oxygen 2 termination. So small polaron on the tantalum transition metal side. So let's look a bit closer to this material. This is a perovskite, and if we do a simple valence state model, we can see that we have oxygen 2 minus, potassium 1 plus, tantalum 5 plus, and if we consider this material made up as a layered structure, layer of potassium and oxygen, and tantalum and 2 oxygens, as is shown here, then we see that one layer is negatively charged and one layer is positively charged, and we have this alternate stacking of positive and negative layers, which will correspond to a tantalum oxygen 2 layer, donating 1 electron, half electron to the layer above, half electron to the layer below, half electron per unit cell. If you have a bulk system, you continue like this everywhere in your universe. But if you have a surface cut, then here you have vacuum. This tantalum oxygen 2 layer only donates half of the electron here, but is left with 1/2 of electron, which does not find any good place where to go. So there is some uncompensated charge of 1/2 electron per unit cell. Here is what could happen. This half of electron per unit cell actually forms a two-dimensional electron gas. You see, it's pretty much delocalized, so it's delocalized, and it goes up to the third layer, kind of. Then these layers are already bulk-like, where this state doesn't appear so much. And these electrons occupy the bottom of the conduction band with decreasing intensity as soon you go deeper and deeper into your slab. But actually, what we propose is a different paradigm, to a different scheme, which is able to accommodate this charge in a better state, which is the polaron formation. Here, all these half of electron per unit cell come together and form one polaron in one particular site. You see here, there is no longer any field state in the conduction band, but you see the formation of a polaronic state in the gap. Of course, it's very well localized, so there is almost nothing in the sublayer and nothing in the third layer. And as I already mentioned, this is the ground state for the system. It's half electron volt better than having a two-dimensional electron gas. And the other thing to notice is that we don't need any defect to form this polaron. It's just there because there is uncompensated charge intrinsically on this material, just when you cut the bulk and you obtain a surface. That's why I call it intrinsic polaron. So why is it important to consider the two-dimensional electron gas? Well, because it's true that this is the ground state of the system. You have a polaron, and then you have the formation of this polaronic gap, polaronic peak. But what happened now if you put more electrons in your system? You can always dope your system, right? And if you look at the experimental STS spectrum, you see actually valence band, conduction band, and a polaronic peak. Is a bit more structure. Actually, this could be explained too. But essentially, these are polaronic state. And then there is a two-dimensional like occupancy of the bottom of the conduction band. And this is due to the excess doping introduced into the system. In this case was calcium doping, which brings more electron into potassium tantalate. And if we consider the same with density functional theory, we have the polaronic state, and then we add more electrons, and we also obtain that the more electrons we put, the more they form like a dispersed gas which occupies the bottom of the conduction band. So to see this polaronic peak in the calculations, you have to be careful and start to put some distortions there, otherwise you get the worst solution, which is with the delocalized electron. And in the experiment, you have to investigate up to low energies with respect to the Fermi energies. Otherwise, you only focus on the two-dimensional electron gas. I didn't tell you everything about this. This is actually a bipolaron. So it takes half electron from 4 unit cells. So there are 2 excess electrons. They come together and they localize on this side. And I will say this is kind of a genuine small electron bipolaron because it doesn't involve any dimerization of surrounding atoms. This is actually the same as a small polaron, small single polaron, where you have one electronic charge localizing there, deforming a bit the lattice bond, but the difference is down that you have 2 electrons. And these 2 electrons can actually dissociate and form 2 single polarons. Single polarons are better localized in the sublayer surface, the subsurface layer. And the energies of these 2 objects and this single double polaron, it's kind of equivalent. But I will say that the formation of bipolarons is favored by considering the effect that they need less space in your surface. So you can reach higher density of polaron formation when you have bipolarons rather than having single polarons. And final consideration is on the effect of these polarons on the potassium tantalate surface. Again, we did experiment, or our collaborators did the experiment, putting CO on potassium tantalate. Here we have the KO island, which we don't consider now, but we focus on the tantalum dioxide termination, and we see that there are spots on it which are either dark or bright, and these are CO molecules that we put there. So one could ask why there are 2 different types of spots if we only have 1 type of CO molecules. Of course, it's because we have somewhere a polaron underneath, somewhere we don't. And when we have a bipolar underneath, there is a strong charge transfer, and we see this guy dark. And when there is no polaron, then this guy is brighter. So it doesn't sound so amazing. It sounds like the same as we have seen before for titanium dioxide, but actually it's not like this. This is experimental AFM. Before was STM. So in STM, you measure the charge, and it's obvious that you get bright and dark when you have polaron and not. Here, the different contrast is given by the fact that the charge goes into the molecule and modifies the lattice bond and also the stiffness of the molecule. So when the AFM tip goes there, it feels this different stiffness and gives rise to different contrast in the image. So this was everything I want to talk about. So basically, basic properties of the polaron formation in titanium dioxide and the effect on the reconstruction and adsorption. Also suggesting some new method we are exploring now. And then finally, something very new, exciting, on the potassium tantalate and formation of intrinsic bipolar. So I would like to thank again all the collaborators, which are all in this picture, except for Georg and Cesare, who were working probably somewhere else in the meantime. So thanks to Zishan, Igor, Martin, Michael, Ulrike, and you for your attention.
Thank you for this very nice talk. Questions?
Okay, thank you. Very interesting. I would have a question on the CO interacting with the polaron. So in our original paper, the interpretation was that the shift in the frequency is due to the interaction with the defect. So we had calculations for the next titanium atom and the second next and the third next. So your interpretation would be it's an interaction with the polaron. So do these 2 pictures contradict each other, or is it just stating the same thing in different words?
No, actually, I think they're pretty much in agreement because, so what I show here is having a polaron below the CO,
Yeah.
and that's something new, okay?
Yeah.
And the polaron and the oxygen vacancies. Okay, but these other points here as done the way you described already. So it's like moving the CO far away from the polaron and the oxygen vacancy too. The difference is that we exclude these 2 points because they are very unfavorable in energy. So we, if we look at the absorption energy, these 2 points here, which would correspond of having ACO close to the oxygen vacancies, like here or here, and the polaron stays underneath. And these are very unfavorable in energy. So we think these cases do not appear. And we calculate the vibrational frequency in every case, and we exclude these 2 points because they are very unfavorable in energy. And then we are left with basically these that have the same energy or same vibration, and these also the same frequency. Kind of, we say it's too big.
If I may, I would like to add one more point. I cannot do the calculation in my head right now, but if you take our original interpretation, you have like 4 shifted COs per oxygen vacancy, because you have these sites around it. Whereas I think if in your picture you would have an oxygen defect generates 2 polarons, so you would have 2 per side. I think in our paper we did a quantitative analysis, but I have to check that. I just wanted to point that out. That may be a way to distinguish between the 2 cases. Just comparing defect density, assuming that the polarons come from the defects and so on. But I will have to check that. I just wanted to point that out.
Of course, could be we have more defect, more polarons than what we think. But I would say in even this perfect case, ideal case, we have 3, not 2, because we have 2 given by this guy, and also the guy in the oxygen vacancies is also there, and doesn't need polarons to give this frequency. So we have. So we have 1 CO there? Yes. This was also a good point of the paper, actually. We have oxygen vacancies without CO and with VO. There is no polaron there, so if you do field state STM, you don't see them. You can see them, for example, if you do atomic force microscopy. I don't have the images now, but in the paper there are.
Okay, let's go on.
Okay. So I have a question about something you said in the beginning of your talk, namely that it's very important to identify the ground state. And I completely agree with that. If you want to compare with STM experiments, which I think are usually done at low temperature, but applications are not at 10 Kelvin, right? Applications are at room temperature or maybe even slightly elevated temperature. So don't you think that these other configurations, which may differ only by a few tens of milli-eV, could be important?
Yes, I totally agree. I mean, I forgot to say that actually we are interested in low temperature, but I totally agree. When you are high temperature, things are much more complicated, and the opening barrier can be overcome pretty easy, and then you have many more things to consider. I'm happy we work at low temperature.
I would be interested to learn more about potassium tantalum oxide. What functional did you use? Did you have a U, and how strong does it have to be to localize? And do you have a spin configuration? Is the spin-orbit coupling important in that case? If you could elaborate a little bit.
Yeah, so we did density functional theory plus U. This slab is pretty big, so I think it would be too demanding to do HSC. I don't know. Let's see. The U was chosen such that it satisfies the experimental band gap is satisfied in the bulk for this material, and we did it for different functionals, PB and scan. And actually, they all give the same results. Then we try to play around with the U. Qualitatively, the result is always there. What you can change is only how much more favorable the polaron is with respect to the two-dimensional electron gas. But it's half electron volt with a U of 4, and which I think it's a fair assumption. And half electron volt is quite big. If you look at our polaron formation energies in titanium dioxide, where we also use a U of 4, the energies less are much smaller than 0.5. So I would say it's pretty safe to say that there is polaron there. And
how about spin-orbit coupling? Does spin-orbit coupling play a role?
We didn't do it on the surface, but we did some calculations in the bulk, but they didn't change. We were looking just at the agreement of the band gap, and adding spin-orbit coupling didn't change much the band gap. And regarding the spin alignment of the bipolaron, this is spin-up bipolaron. The transition metal side likes to maximize the spin, so they go up, up.
If I may, I also would have a question about the machine learning. So what is kind of your descriptor that goes into the machine learning?
So the descriptors are the distance between a polaron and a vacancy, because we think this is an important interaction. Then the distance of a polaron with some other polarons which are in a certain cutoff or something like this. And then also the density of polarons on every layer.
So you are disclosing now
all the ingredients. So, sorry, Victor, you have to be faster. It's to put some pressure on Victor, has to be faster now.
But the machine learning does not predict you an actual structure, right? It's too coarse for doing
No,
that. It's just, yeah.
It's
so how can it capture the energy if it does not capture the actual structure?
So,
because
no, actually,
the relaxations are very important.
So I didn't spend a lot
systems,
of
right?
time on explaining it. The way it works is such that you have to do some DFT calculations. You have to do it. Then you train the machine to work such that, given this input, so this distance of the polaron defect, distance of polaron, and so on, given these inputs, then this is the energy I want you, machine, to give me. And then I get trained like this till we get a satisfied agreement. And at the end, we test the machine on completely new set of polaronic configurations, and we get this curve I showed you before.
So just following that, so it's just got 3 variables and you fit a function that produces an energy?
No, actually,
I mean,
so this is the main idea behind it, and the
yeah.
technicalities are much more complicated. And I'm not
but if
even...
the vector is 3 numbers and the output vector is 1 number, you've just fitted a nonlinear function with 3 variables.
But it's more because you have more defects, you have more polarons, not just 3 numbers. These are just 3 quantities, but you have to consider them, considering all the multiple interactions.
But it's phenomenological based on just the...
Yes.
Yeah,
We know what is important from the system, and we apply this. We take this as ingredients. We are trying to also to extend, to make our machine like more universal, and then that you just have to have the intuition how to tune the interactions, and then you can describe different systems. But
have you tried plotting these functions to see whether they, reproduce physical expectations of?
I think we didn't, but that's a good suggestion indeed.
Thank you.
Thank you. Because before I take the next question, I also have a question. Can you go on slide 9? Because I was puzzled a little bit by your electronic structure, so I would like to ask you some clarification. Yes. So this is rutile, right?
Yes.
And this is valence band and conduction band plus the defect state in the gap. So the gap, to me, is too small. It's only 1.2 eV.
Yes, okay.
And then the peak is very close to the valence band, whereas we know when you add an electron, it's very close to the conduction. So can you please explain what is this?
No, completely. We actually didn't put this on any paper. I just chose this image because it was easier to present. But this image was obtained like with the trick, which was removing 1 electron from the slab. So
then you make a hole. Then it's
no. Then we remove 1 electron. We don't have 2 polarons here, but only 1 polaron. And then we have
polaron associated to the hole.
No,
Is the unpaired electron sits on an oxygen. I'm sorry, that is an oxygen state then.
No. This is a polaron on the titanium side.
No, cannot be.
That's a
If
field state. That's a field state.
Cannot be. If you remove one electron from your model, you'll get this
Yes.
state will.
So we
This
have
electron will come from the valence band.
we have
Then
one
you-
oxygen vacancy.
You have an oxygen.
We have the oxygen vacancy. Okay.
Then you didn't say.
Yes. Sorry. We have so in
Oxygen,
principle.
and then you remove one electron.
So we have two borons.
So you have only one titanium 3 plus in the vacuum.
Yes.
Yeah, but that again is
It's
too
more
close to
because
the-
when you remove one electron, you need to add a positive background charge
So it's
to
totally.
make this.
Okay,
So
I understand.
so you cannot look at
But
the.
so don't show this again, please, because it's really,
But
I think it's something
what-
because this gap is too small. This state is in the wrong place. So
You showed for the potassium tantalate that the bipolaron and the two separate polarons you said are degenerate, right? Have the same energy.
Sorry?
The bipolaron in potassium tantalate and the two single polarons have the same energy, you said?
yeah, it's quite kind of similar energies. Yes.
And do you have an opinion what would happen if you added more electrons, if maybe the bipolaron could win if you added more electrons?
No, I don't think so. I mean, I'm not sure because there are already a lot of them on the surface. There is one every 4, and there is one every 1 side in the other direction, which is the best configuration we found to have this arrangement of bipolarons. And also the experimental AFM show that there are stripes of these black spots. So I think that's already the maximum concentration of bipolarons we can have. Okay, and I try to localize more polarons by adding extra electron, and there seems to be only single electrons after this.
Always on the tantalate, so very basic. I don't understand, where are these excess electrons coming from?
From the fact that there is some uncompensated charge at the.
So it's not reconstructed,
The surface.
So there is no the steps that you discussed which are discussed in the science paper.
Yes. So I think we are in an intermediate case where we have some kind of terraces of tantalum dioxide of intermediate size. Okay, so somewhere between this and this. I think
So
they.
you model that as
We only focus on the yes.
a purely.
Yes, and actually in this, when we,
Compensated, there must be something to be
yes, but
compensated.
when we did this paper, we model it. Also, the case of having a tantalum terrace and the potassium island, and when we went to very large sizes, then we saw the formation of the two-dimensional electron gas in this case.
Yeah.
Okay, so.